This meeting is being recorded.
I guess you have muted yourself, sir. Unmute. Yeah, now you are audible.
Okay, so today's session is we are going to talk about circuit design processes. Basically, the intention of this session is to cover the major part of this topic is stick diagram. So we will focus on that stick diagram. But before going towards the stick diagram, we'll cover some uh, basic points related to that. So in this session, what I'm going to cover is CMOS layer. So first we will discuss about what are the layers or what is the fabrication process in short, not in detail. Uh, then the design rules and layouts, and at last we will discuss about stick diagrams. Okay, so that is these are the contents of this session. So starting from layers, then rules, and then lastly we'll discuss about stick diagram. So let's talk about layers first. So fabrication layers, the process involves um, various steps. So starting from the processing of the substrate, then the SiO2 layer, then photoresist, mask, etching regions, then creation of gate, source and drain, and at last metal layer. So let me annotate here. I will just show you by annotating itself. So when you are talking about substrate, right? So suppose we are designing NMOS. So for NMOS, what you have to which substrate you will use. So P substrate we will use, right? So this is our substrate. So this is P substrate, and P substrate means uh, uh, the P type of impurity we will use here, and this substrate we will build on the silicon wafer. So silicon wafer is the base. Silicon wafer is the base, we can say. In this base, on this base, we will build this substrate. Okay, so Si wafer, silicon wafer. Then P substrate contains, so here we will build N channel. Okay, to design NMOS, inside the P substrate we will require N channel. So first uh, layer we can say is substrate layer. So substrate we have built, that is P substrate. Then next is SiO2 layer. So on this substrate we will build the SiO2 layer, silicon dioxide. So what is the purpose of this SiO2 layer? So to prevent uh, the damage done to the wafer, or to um, we can say to separate out transistors, to maintain the gaps between some transistors, and to maintain their scalability, and to protect the your wafer, we use this SiO2 layer. So that is the importance of SiO2 layer. The similar way, the third layer is there, that is photoresist. So after this SiO2 layer, this is second, which is SiO2. After this SiO2, we are having photoresist. So after this, we are having photoresist layer. So photoresist layer, as name indicates, it is light sensitive layer. Okay, so when some lights are falling into the wafer, so it may change the functionality of the design, right? It may change the functionality of the your circuit. So it should not affect the functionality. That is our main purpose. So photoresist layer will be used to protect your circuit and to pass particular amount of light only, that is UV light, ultraviolet light. So for that we use this photoresist layer. Okay, so the third layer is photoresist. The first layer is your substrate on the wafer, then SiO2, then photoresist. After that, mask is there. Now, what is mask? Mask is nothing but we can say it is like a trace paper. Have you used trace paper? So we just build some design on the trace paper, and then we just put that on the white paper, and that design will get press on that trace paper. That design will get printed on that white paper, right? So the same way this mask will work. So it has some design patterns on that. So here we will use the mask. And some design patterns will be there on this mask. And when UV light falls on that mask, so this is UV light. So when UV light passes through this mask, so on that particular design part, so suppose this is, let me finish this drawing first. Okay, so let's suppose this is UV light. It is falling on this. So the exposed area, the area which is exposed to UV light, that will remain as it is. So exposed area to UV light will remains on the wafer, and unexposed area to UV light will get removed. So this is important point. So whatever area which is exposed to UV light, that will remain on the vapor, and the unexposed area, suppose this area is unexposed, it is not exposed to UV light. This area is not exposed to UV light, so it will remain, it will get removed from this vapor. So that is the function of this mask. So mask will transfer your UV light towards your photoresist. So this layer after the mask is photoresist, and after the photoresist we have SiO2. Okay, so this is the purpose of mask. Then etching the regions. So after the photoresist, your now if you are considering this type of design, so after the masking, your design or your substrate will look like this. Okay, like this. Because this is unexposed area, so it will get removed, this middle part. Okay, so this is and what is etching? Etching is nothing but the regions which are there. So just we have to cut the unnecessary part and smooth that area, remove some we can say cleaning the wafer. Okay, that is nothing but etching the regions. After that, there is a creation of gate. Now to create the gate, we have to use one more layer on this. After this photoresist and all, once this process is done, we will put, to create the gate, we will put polysilicon layer on this, polysilicon layer. We will use polysilicon for the gate. So this polysilicon layer is used for the formation of the gate. After that, creation of source and drain. Now to create source and drain, since it is N channel, we will diffuse N type of impurity inside this substrate. So N type of impurity inside this substrate. Since it is N channel, so we will diffuse N type of impurity in this. So it is called as diffusion. So to create source and drain, we have to use diffusion process. And at last, we will use metal layer, which is the metal which we are using is aluminum metal we are using, which is used to provide the insulation as well as conduction function. Conduction, it will take care of conduction as well as insulation part. So some part of your substrate, some part of your NMOS is conducting in nature, some part is insulating in nature. So that will be taken care by this metal layer. So that is the use of metal layer. So once again, I will go step by step about the fabrication process. So first is creation of the substrate. First, you have to create the substrate, whatever substrate. If you are designing NMOS, you have to use P substrate. Inside the P substrate, you have to create N channel. Then SiO2 layer. After that, P substrate we will use. So P substrate will be formed on silicon wafer. Silicon is best for designing of your semiconductor devices. That's why we are using silicon. Then SiO2 layer will protect your circuit, will maintain the scalability. Then photoresist will keep your will act as a we can say medium for transferring your UV light towards your substrate. Mask will help to expose the part which is required and unexpose the part which is not required. So unexposed part will get removed and exposed part, so the part which is exposed to UV light will remain on the wafer, Then etching the regions. Once this masking is done, there should be some cleaning, there should be some we can say your design should look perfect. Scalability, it should have some scalability also, so that can be checked, that can be modified using the etching process. Then creation of the gate. So for gate we use polysilicon. Okay, polysilicon is required for creation of the gate. Then creation of source and drain. So source and drain, since we are designing, we are dealing with N channel, so we have to insert the N type of impurities in this channel, right? So that's why the using the diffusion process we insert the N type of impurities in this substrate using the diffusion process, and which will form the source and drain of that MOS. And at last we will use metal layer of aluminum, which will protect your circuit from the damage, other damages, and to protect the transistor also, because after some years the size of the transistor, the functionality of the transistor the functionality of the transistor may get changed, right? So that is the purpose of using metal layer. So this is all about regarding the fabrication, the layers of the CMOS layers. Okay, that is the point which I wanted to discuss. Okay. Then next comes is the design rules and layouts. So what is a design rule? Design rules are not, what are the design rules? They are nothing but a set of geometrical specification that represent the design of the layout. So where to place your component, what should be the height, what should be the width, okay, what should be the gap between the two components. So it is kind of a layout, it is kind of a top view of your chip. So how your chip will look, okay. So that is the you can say it is a top view of your chip. Now as I said, we are going to discuss about stick diagram, so it is associated with stick diagram as well as layout, and it gives the placement of different components and their connection in detail, but the dimension of the devices are not mentioned in the stick diagram. So we'll talk about this stick diagram later. Fabrication process needs different masks. These masks are prepared from the layout. As I said, mask is nothing but like a blueprint, we can say, just like a trace paper, the rough design, and these different your chip contains different components, and they are having separate mask. So at particular component, for particular component we will use one mask, for another placement of components, for grouping the components together we will use another mask, like that. So multiple masks at multiple stages we will require. Then layout is the interface between the circuit designer and fabrication engineer. So the as I said, layout is nothing but a blueprint. So what you are going to design, so that will come from the circuit designer, and the layout will be taken out by the fabrication engineer, who is actually performing the fabrication process till the last. So that's why it is interface between circuit designer and fabrication engineer, and it is made up of design rules, like, right? Because some layouts, if you are designing any layout, it should have some rules. And these rules usually specify the minimum allowable widths for physical objects on the chip. So for example, just a minute, I'll annotate once again. So this is your chip, and this is NMOS, and this is PMOS. Okay, so what should be the distance between the connections of NMOS and PMOS? Whether we can place like this, very near to each other, or what distance is maximum allowable distance between the NMOS and PMOS. So such type of things will come into picture when you are talking about the rules. Okay, then we are having various layers also, like metal, polysilicon, then diffusion areas, then minimum feature dimension. Feature means transistor, we can say various components available on the chip. Okay, their sizes and all. Then minimum allowable separation between the two features. Okay, so that is why we require the design rules. Okay, so why we require design rules? So if design rules are followed, so we can achieve better efficiency, then increase the probability of fabricating a successful product on silicon wafer, and your circuit will get better, it will have the better reliability. Okay, so that is the advantages of using design rules. And if they are not getting followed, then the design consuming the consumption of silicon area will be larger, because you are placing randomly the components. There is no rules you are following, so the components are getting placed randomly, so they may require larger space, larger area of silicon. The device can fail during or after the simulation, so that is the chances of failure of the device if you are not following the design rules. And lastly, the functional or non-functional circuit. So the circuit may function according to the requirement. It may function according to the requirement, or according to the functionality given by the circuit designer. Or it may not work according. It may behave differently. Your circuit may behave differently. So that is a disadvantage of not following this design rule. So generally, in all the cases, you have to follow the design rules. Then types of layout design rules. So basically there are multiple types, like micron rule and lambda based design rule. Micron rule are, if you are using micron rule, then all device dimensions are expressed in terms of absolute dimension, that is micrometer by nanometer. These rules will not support proportional scaling. So generally, if you are using micron rule, they will not support the proportional scaling. What is proportional scaling? So if you are reducing the size of one component, in proportion to that, the size of the other component should also get reduced. Okay, that is called as proportional scaling. So if you are using micron rule, then they will not support this proportional scaling. Then next we will go for lambda based. Actually, it should be lambda. Maybe that is getting out from this PPT. That's why it is not visible properly. The lambda, it is lambda. So lambda based design rules. So these rules are more preferable than micron rule. So it is developed by Mead and Kenway. All the device dimensions are expressed in terms of a scalable parameter, lambda. As I said, the scalability should be there. So if the size of one component we have reduced, in proportion to that, the size of another component should also be there. That is called as scalability. So there is one common factor is there, which is lambda. And using this common factor, we will place the component. So in terms of multiples of this lambda. And how is the lambda is defined? It is defined by L by 2, where L is minimum feature size of the transistor. So what is the transistor is there and its feature size of the transistor. So the minimum feature size of the transistor is L. L divided by 2 is lambda. That means L is equal to 2 lambda. So the minimum feature size of your transistor should be 2 lambda. So the smallest part of your chip, should have the size 2 lambda. Okay, 2 lambda. This rule supports the proportional scaling. As I said, in comparison with micron rule, the lambda based rule supports the proportional scaling, where micron rule doesn't support the proportional scaling. So that is the difference between lambda based and micron rule. Then, as I said, minimum length or width of your feature means transistor or some component of your circuit, not only transistor, some component of your circuit, and its minimum length or width should be 2 lambda to allow the sharp contraction. To allow the the minimum separation of the feature on the layer is also 2 lambda. So the separation between the two features, two transistors or one transistor, one another component, capacitor, like this. So the minimum allowable length should be 2 lambda to ensure the adequate continuity of the inverting materials. Okay, now two features on the different mask layer can be misaligned by a maximum of 2 lambda on the wafer. So different mask layers also we can measure the difference between distance between the features on the different mask layer. As I said, we have to use multiple masks in the fabrication process, and during that process, the distance between the components also matters. So when you are using multiple mask layers, so the distance between the two components in multiple mask layers also should be maximum of 2 lambda. That is the meaning of this line. Then if the overlap of two different mask layers can be catastrophic to the design, they must be separated by at least 2 lambda. What is the meaning of this? So if there is a overlapping between the two mask layers, so distance between the two component or the two features on that two different mask layers which are overlapping, this should be at least 2 lambda. This should be also at least 2 lambda. So whenever you are talking about lambda, just keep in mind 2 lambda. Okay, not just a lambda, 2 lambda. 2 lambda should be the minimum size of the feature. 2 lambda should be the minimum allowable distance between the two features, like this. If the overlap is just undesirable, they must be separated by at least lambda. So if there is a problem in the overlapping is not complete overlapping, so at least they must be separated by lambda. If the overlapping is complete overlapping, then they should be separated by 2 lambda. Otherwise, if there is some disturbance in the overlapping, they are not completely overlapped, then they must be separated by at least lambda. Then using this, we can show here. So rules for N-well. Now what is this well? I will talk later when we will talk the stick diagram. So similar to NMOS, we discuss about NMOS. Right now only I will talk about the well, so that we will get. Okay, so previously we have talked about NMOS fabrication. So in NMOS, we have substrate, P substrate, and N channel. For PMOS, what we'll do, N substrate and P channel, right? So instead of calling it N substrate, we call it as N well. Okay, N well. That is the meaning of well. So we create a substrate like thing around this P channel, and that is nothing but N well. That is the meaning of N well here. So minimum width we should be 10 lambda. So these are the general rules that you have to follow for designing the wells. Wells at the same potential with spacing. So if there is same potential with spacing is there, so 6 lambda wells at the same potential, but there is no spacing, then their distance should be 0 lambda. Then wells of different type with spacing 8 lambda. So no need to just mug up these things and all. Just you have to keep in mind in general things. They are not going to ask in detail. I'm just telling these things for the information. Then rules for active area. So what is active area? The area which contains the electrons and holes. So they are actually conducting. The surrounding area is not, we don't call it as a active. The area which contains the electrons and holes, okay, and they are actually carrying the electricity. They are taking part in the conduction. So is nothing but an active area. So minimum width should be 3 lambda. Minimum spacing between the two active areas should be 3 lambda. Then source, whether the active areas of source or drain. So it's distance between that active area to the well edge. So as I said, well is nothing but like a surrounding only, right? It is like a surrounding only. So this is your well, okay, and this is your active area. So let's say it is source and drain. Okay, source drain. So its width should be height, which should be 3 lambda. The spacing should be 3 lambda. And the distance between this active area to the edge, this should be 5 lambda. Similarly, well contact active to well edge should be 3 lambda. So these are the different lambda rules that you have to take care while designing. But as I said, you will require this when you are actually working on hardware system. But you should know these things. Then rules for poly 1. So minimum, as I said, poly silicon is required to create the gate. So minimum width should be 2 lambda, spacing should be 2 lambda, gate extension of active. So there should be some extension to provide some additional connections to the circuit. So that is called as gate extension for additional connection. So it is also minimum extension should also be 2 lambda. Then minimum field poly to active should be 1 lambda. Okay, it is shown in the figure. Then rules for contact to poly 1. So exact contact size is 2 lambda by 2 lambda. Actually, it is cross 2 lambda by 2 lambda. So width and height of this contact should be 2 lambda by 2 lambda. Then minimum poly 1 overlap is 1 lambda. Minimum contact spacing is 2 lambda. So contact between the two the spacing between the two contacts should be 2 lambda. Then this is one of the PMOS, one of the NMOS structure where some lambda things are mentioned. So all mask dimension are based on multiples of lambda. That is polysilicon minimum width is 2 lambda. So this red color indicates the polysilicon. This red color vertical line indicates the polysilicon. Its minimum width should be 2 lambda. Then minimum metal to metal spacing is 3 lambda. So metal to metal spacing should be 3 lambda. So this is metal. The blue color indicates the metal. Blue color indicates the metal. Now, after talking the lambda rules, we will discuss about stick diagram. And this is the important point that we have to cover in this session. Okay, so stick diagram is symbolic representation of the layout. In stick diagram, each conductive layer is represented by line of distinct color. So there are some colors that are differentiated with respect to function. Then width of the line is not important. They just give the information about the wiring and the routing information. Then does all the components wise relative placement. So they will place your component relatively, but they will not show exact placement, exact transistor sizes, exact wire lengths, exact wire widths. So dimension is not a constant when you are dealing with stick diagram. They are just a rough estimate. Okay, just a rough estimate to the actual layout. Then there are some rules. So you have to use different colors. So for drawing the VDD and ground, we have to use blue color that will get indicated by blue color. So I will just annotate here. Okay, so just so this is VDD and this is ground. There should be enough spacing between these two. Then a demarcation line is there at the center, which is of brown color. So it will separate between the VDD and ground. This is demarcation line. This line will separate the wells. So N well, P well. As I said, if you are dealing on the top, if you are having the PMOS, so it contains the N well, and for NMOS it contains the P substrate, that is P well. Okay, so between the between the wells, this line will divide this. This line will represent the well, or it will separate these wells. Then next, active paths must be drawn for requirement of pull up and pull down transistor above and below the demarcation line. What it indicates, the above part is pull up part. So above the demarcation line will be pull up part, and below they will be pull down part, because in normally we use PMOS on the top and NMOS on the bottom, because PMOS will pull up and NMOS will pull down. Okay. Then draw vertical poly crossing both the diffusion. So we are having diffusion lines here. So just a minute. Green. Yes. So this is N diffusion. And this is P diffusion. Sorry. This is N diffusion, yellow color, and green color. So diffusion layer, and then a red color line indicating the polysilicon will be crossing these diffusion lines. So this red color line indicates the polysilicon. So remember, the poly or red crosses active, green or yellow where the transistor is required. So these are the transistor. That means it is crossing here twice. So here one transistor is there, here one transistor is there. Okay, so on the crossing of the red color with either yellow or green, there the transistor exists. There the transistor exists. Okay, so this is the meaning. So where the transistor will be located actually at these points. So where this line is crossing here, or we can denote it by cross. Contact is denoted by cross. Okay. So this is how the general representation of stick diagram. So first you have to draw VDD and ground, then demarcation line, then diffusion lines, and then polysilicon line. Polysilicon line will cross the yellow and green line. Okay, where it represent the crossing represent the transistors. Okay, so let's move ahead. Okay, I think we are good to go towards this first circuit, which is CMOS inverter. So as you know, the inverter is nothing but it will invert the input. So if the input is up, it will be down. If the input is down, it will be up. So 1 0 0 1 like this. Now, in case of CMOS inverter, we have to use one PMOS and one NMOS. So first is your PMOS, and then the downside, which is acting as pull down, will be your NMOS. So as I said here, this is your PMOS, this is NMOS, this is source, this is drain, this is gate. In case of NMOS, this is drain, this is gate, this is source. Okay, remember this. For PMOS, source, drain, gate, drain. For NMOS, drain, gate, source. Okay. The upper part is, this part is pull up part, this is pull down part. Now, how to draw the stick diagram for this? Let me go to the next slide. Okay, so they have already drawn this, but I will show you once again. So we will draw the circuit once again here. So this is I have directly mentioned in the PPT, but we will draw once again. So this is your VDD. This is VDD line. This is ground line. This is your input. This is your output. Then this is PMOS. So this will be source. This will be gate. This will be drain. Below is drain, gate, and source. Now we'll draw the lines. So we'll take the colors. So first you have to draw VDD and ground. VDD and ground. Then draw demarcation line. You can show it by dotted lines. Okay, after this, we will draw the polysilicon line. So they have shown like this. We can show in our way also. So first we will draw the N diffusion line. You can show this way also, N diffusion, and a green color. This is P diffusion. Okay, after this, we will draw the polysilicon line. Now, how many polysilicon lines you will draw? So there is a trick. Okay, there is a trick. See, how many variables, input variables are there? Only one. So you have to draw only one line. If there are two variables, for example, A and B, two inputs, A and B, then you have to draw two polysilicon lines. If there are three variables, A, B, C, you have to draw three polysilicon lines. That means three red lines. So if there is only one red, if there is only one variable, input variable, so you have to draw only one red line. So this trick you have to remember to draw the stick diagram easily. Okay. So A is only one input is there. So we'll draw only one red color line. Okay. So this is the one red color line I have drawn. Now, the naming I will do by black color here. So this is the source of this transistor, which is PMOS. So this is PMOS and this is NMOS. So this side of this red color line, we are consider it is not a rule. Okay, it is not a rule. I'm considering this as a source and this is as a drain. So source is connected to VDD, source of this PMOS. So this transistor is getting represented by which one? By this one. And this transistor is getting represented by this connection. Okay. So just keep that in mind. So source of this PMOS is connected to VDD, right? Source of this PMOS is connected to VDD. So we'll connect this source to VDD. So there is a connection. That means we will make a contact. Contact is represented by cross. Contact is represented by cross. Contact is represented by cross. So source is connected to VDD. Source is connected to VDD. Now drain is connected to drain of this. So both drain are connected. So here there is a NMOS at below. So source and drain. Source and drain. And they are connected. So how you will connect this? Using a metal. And metal is represented by blue color line. So these two drains are connected. So we'll make a connection between these two drains. How to make connection? Just put the line and make a cross. Okay, that means they are connected. These two drains are connected. So see, drain of this PMOS and drain of this NMOS, they are connected. And there is output. So this output also, this metal also we have to extend to show the output. This metal, right? Now the source of the below, that is NMOS, is connected. Where it is connected? It is connected to ground. Source is connected to ground. So that's why we will connect this source to ground. Sorry, we'll use. Okay, can use blue also. No issue. We can use blue for the connections. Yes. Okay, so this is how our stick diagram, and where will be this A. So this whole line is representing A only. So no need to mention. When we will simulate, we will put that on this red color line only. We will put the inputs on this red color line only. So no need to mention the separate connections for A. Okay, when we will do this on the software, simulation software, we will mention the input on this red color line only. That's why the same thing I'm doing here. So just I'm mentioning this as a A. No need to mention any separate connection for A. Because this red color line is representing gate only. As I said during the fabrication steps, for designing the gate, we use polysilicon. So this red color line is nothing but polysilicon. Understood? So this is how these both diagrams are same only. I have drawn this in slightly different manner, but they are same. Here also, here they have mentioned the input. I have taken it from the one of the books of the CMOS, where they have mentioned like that. But it's fine. We can do this way also. Okay, so both are same. So if you are having any doubt in this, please let me know. Otherwise, we will see the different example, and we will see the simulation of this also, because we are having ample time. Still 1 hour is remaining, so we can do a lot of examples. Once again, I will explain this. See, we are designing CMOS. So first, So first is our PMOS and then NMOS. Here input, here output, VDD, ground, source, gate, drain, drain, gate, source. Now you have to draw two lines. First for VDD, then for ground, then for diffusion, yellow for N diffusion, sorry, it will be P diffusion because this is PMOS, and here the green color. Then the polysilicon. So as I said, polysilicon will depend number of polysilicon, number of red color line depends on number of input variables or number of inputs. So here there is only one input. That's why we'll use only one red color line, which is indicating the input. Now, next comes your source and drain. So this is nothing but the initial connection, the top connection representing the PMOS and the bottom connection representing the NMOS. Bottom crossing represent the NMOS. So source, drain, here source, drain. Okay, then the source of the PMOS is connected to VDD. Source of PMOS is connected to VDD. Drain of PMOS and drain of NMOS, they are interconnected using metal. And the output is also from this connection only, drain connection. So to indicate the output, we will extend this metal here, and here we'll write Y. And the source of the NMOS is connected to ground. That's it. Okay, so this is how a simple stick diagram for CMOS inverter circuit we have built it. So if you are taking notes, please use different colors so that you will not get confused, because there are color codes for the drawing the stick diagram, and if you follow that color codes, it will be beneficial. Okay, so this is about the CMOS inverter. So the same thing in the simulation we'll study. So when we will run this the simulation software, I will explain these things. So as I said, the upper part is the PMOS part, the lower part is the NMOS part, and in the simulation software, your circuit will look like this. Your circuit of CMOS inverter will look like this. So as I said, the upper part is PMOS. So for PMOS, the substrate is N substrate. So we call it as an N well. And the below part is the NMOS. So there is a P substrate we are using. Then middle line is nothing but a polysilicon line. It is indicating the gate or the polysilicon. Then there is a diffusion material, which is called as active region, this green color part. So P for PMOS, the P diffusion we will use. For NMOS, the N diffusion we will use. Remember that two lines we have drawn. Okay, so the same thing, the yellow color and the green color. So upper is the yellow color which indicates the P diffusion, and the green color which indicates the N diffusion. And the connection between these can be done by using blue color metal. And this white color are called as contacts. Okay, so the same circuit will look like this in the software. We will after this we will go towards the software and we will implement the circuits there. Now let's draw some stick diagrams here. So suppose I want to draw the CMOS NAND gate. Okay, CMOS NAND gate. So what is the A dot B bar? Remember, the CMOS, the output is always complementary. So if you are using A and B as an input, so CMOS will generate them as a complemented output. So if A is the input, CMOS inverter, the output will be A bar. So CMOS circuit will always implement the circuit like that. Okay, so accordingly, we have to take the input. So if you are taking input AB, then accordingly you have to design the circuit such that you will get the output as a NAND gate. A dot B bar. So it is representing the NAND gate. Now, how you will generate this NAND gate? So see, you have to keep some in series, some in parallel. So this as a shortcut you can remember P dot P. Only one thing you have to remember. Only one thing you can keep in mind. P dot P. What it indicates? What it indicates? So if there is a PMOS and if there is a AND operator, so there they will be in parallel. So the meaning of this is, if it is a PMOS and dot operator, they will be in parallel, and the rest of the combination you can decide accordingly. Okay, so there is a, so those who will get confused or who will get who are not getting proper timing in the exam, suppose you are running very short in the time and you have to manage whole thing within a 5 minutes, 10 minutes, so you can remember this trick. So if PMOS is there and if dot operator is there, that means AND operator, you have to keep that transistors in parallel. Okay, so P dot P, only one. Once you remember this, the rest of the combination you can decide because they are opposite, right? So I will just show you that table here. So PMOS, NMOS, you can note this table somewhere in your notebook. If it is dot operator and or if it is plus operator. So and or. So this is and operator and this is or operator. So if it is AND operator, the transistors will be in parallel, as I said. So P dot P, PMOS dot parallel. If there is OR operator and if it is PMOS, they will be in series. And for NMOS, it is exactly opposite. So if NMOS is there and if AND operator is there, they will be in series. Otherwise, they will be in parallel. So this table is very important. If you are running, it has no logic, no technical logic. Okay, I am again telling. It has no technical logic, but just for remembrance purpose, I am telling how to remember to draw a circuit diagram.
नहीं मेरे को चलता है तो
Yes, Tejas. Okay, so here what I'm want to tell you is, if you remember this table, it has no technical background, just for remembrance purpose I'm telling this. So for PMOS, for dot operator we put in parallel, for plus operator we put in series, for NMOS series and parallel. So accordingly, we will design a circuit. So here it is a dot operator, right? So our PMOS should be in parallel. So we'll keep the PMOS in parallel. So these are our PMOS in parallel. A, B are the inputs. This is VDD. This is our PMOS. Since it is dot operator, that's why we are putting PMOS in parallel. And the NMOS, they are in series. And the output should be between NMOS and PMOS. The output should be between NMOS and PMOS. So this is our output. The output is F, so we'll mention it as a F. Okay, so this is the circuit diagram. First you have to draw correct circuit diagram, then only we'll draw correct stick diagram. अगर आपने circuit diagram if you have missed the circuit diagram, if you have not drawn circuit diagram properly, then your stick diagram will get wrong. If your stick diagram will get wrong, your simulation, you will do wrong simulation, you will get wrong result. So starting is from this circuit diagram. Circuit diagram should be proper, it should be correct. Now we'll draw stick diagram for this. So we'll take two blue lines, one for VDD, one for ground. Then we'll take two diffusion lines. So for P-type diffusion, we'll take yellow line. For P-type diffusion, for N-type diffusion, we'll take green line. Okay, so for P diffusion, N diffusion, like this. Then here, see here there are two variables. Here there are two variables A and B, so we'll require two red color lines, two polysilicon lines. So one for A, one for B. This is A, this is B. Now in the diagram I haven't shown the gate. Okay, gate source. So initially this is source, drain, source, drain, source, drain, source. So sources of both the PMOS are connected. Sources of both the PMOS are connected to VDD. So source, and here drain. So the sources of both the PMOS are connected to VDD. That's why I will show the connection like this. The source of this PMOS is connected to VDD. Source of this PMOS is also connected to VDD. And the drains are connected to drain of the A NMOS, A-type NMOS. So they are connected to drain of A-type NMOS. So that means this. So here I will mention this as a source. You can mention here source and drain. Here drain and here source. So you can show like this: drain of this drain of A type of NMOS is connected to drain of A type of PMOS as well as drain of B type of PMOS, right? And on the same wire, on the same connection, there is an output also, which is F. So you can make the connection. So like here I have made the connection. So same way, you can make the connection like this. And here you will mention the output, that is F. Okay, like this. Then the source and drain, they are connected of NMOS, and the source of B type of PMOS is connected to ground. So this is the stick diagram for CMOS NAND gate. Okay, CMOS NAND gate. If you want to draw this in your notebook, you can draw, or you can make a take a photo of this. So in some books, the connection wise it will be function wise it will be same, but connections they may differ because they are of metal. So metal you can extend anywhere, so don't get confused in that. So as I connect drain like this, so it is okay to connect like this because it is metal only. We are using metal only to connect both the drains. We can extend both the drain together and connect them using metal only. So I will show you in Microwind software the same network and its connection also. Okay, so without wasting much time, I will directly go to the software part, and then we will see one more circuit. So hope you note down this table. I just you remember this in your mind. P dot P. That's it. P dot P. If you are running short of time in the exam, you can use this shortcut. PMOS, if it is dot operator, that means parallel. If you remember only one, you can remember rest of the things. You can apply your logic to remember this remaining, because they are exactly opposite. If one is parallel, other is series. So if PMOS, it is parallel. In case of NMOS, it should be series, and vice versa. Okay, so those who want to note down, just note it down in 1 minute, and then we will directly move to the software part. After that, we will see one or two examples again, more examples. First, we will implement the CMOS inverter, and then we will implement this, because that circuit we have seen earlier. So first, we will implement CMOS inverter. Okay, I think you noted it down. If you are having any doubt, you can ask in the chat box. Sir, please repeat again, or if you are not getting anything, you can ask like that. Okay, fine. We'll switch to Microwind now. Just okay. So this is a microwind software. I hope you're aware of that, but still I will explain some part of this. So basic blocks are there, like you can place, wait a minute. Yes. So I'm using here microwind software for running this. So first, if you have to select the foundry, so there is a rule. As I said, the design rules are there. So CMOS 08018 design rule we have to apply. So here you will see that 1 lambda 0.100 micrometer that is written. We are following that. Now here there is a palette. From here you can place your components. So you have to click on MOS generator. And from here,
Sir, your screen is not visible, I guess.
okay, just I think now it may be visible.
Yes, now it is visible.
Okay, so this is the palette where you can place where you can drag your components and place it. We are having various layers as I discussed: N diffusion, P diffusion, N veil, polysilicon, contact, polysilicon to metal 1, metal 2, metal 3, metal 4, 5, 6. So there are various metal layers that are required in fabrication process. But for making the design simple, we'll keep this metal 1 only. Okay, now first we'll design a CMOS inverter. So for that, what we will require, just let me annotate here. We'll require one NMOS and one PMOS. So first I will take NMOS first. So width of NMOS, I think it is fine. Sometimes you have to change this width and length also. Okay, so here I will keep it as it is. Okay, thank you somewhere. Okay, so generate device, just you have to click on generate device and keep your cursor here where you want to place your NMOS. So I have taken NMOS. Now if you want to select that component, you have to click on this scratch and move option and place it properly. Then take one PMOS with, let's say, different size, 3 width. You can vary this width and place it here. You can minimize, maximize, zoom out, zoom in from here. So suppose I want to zoom in. Wait a minute, it's taking time. I'll create a new file. Normally it will not take this much amount of time, but it's okay. So we will have one NMOS. Let me end this and reopen the microwind. Just a minute. So here we'll take NMOS of size place it here, and we'll take PMOS with some increased size, place it here. Then we will move this okay. So while designing, you have to keep the proper distance between the NMOS and PMOS. Okay, keep in mind that you are keeping proper distance between these two, NMOS and PMOS. Since we kept the width more for this, that's why it is looking bigger and NMOS than NMOS. Now, while drawing the stick diagram, so since this is just a minute, this is our CMOS, right? So this is PMOS, this is NMOS, this is VDD, this is A, this is output, this is ground, then this is your source, drain, source, and this is gate. So gates are connected through polysilicon. That's why we have to take the polysilicon and connect the two. Just you have to, using the mouse, you can drag that and you can select that and connect them together. Polysilicon are connected. Now source is connected. Now this part, so this part is representing the source part. So source of PMOS. Okay, source of PMOS and drain of PMOS. This is drain of NMOS and this is source of NMOS. Okay, like this. So source is connected to VDD. So since this blue color is very small, we have to extend this further. And this box is representing the well. Okay, the box is representing, this green color box is nothing but a well. This is a well. Okay, so this is coming inside this well. This blue color box of this source is inside the well. The part is very small, so we have to extend this. So that's why we will keep make this out of this well. It should be out of this well to connect it properly to the VDD. To connect it properly to the VDD. And here I will draw one more metal layer for the VDD connection. So for the VDD, or you can show here also, it will not affect. It will, you can show VDD on that here also. It will not affect. Okay. But still, it is better to extend this metal and show VDD there. Now the drain part is connected to drain of the NMOS. Drain part is connected to drain of NMOS. So here we will extend this drain and we will connect them together. And then we will extend this metal also to show the output like this. And then source of this NMOS is connected to ground. So again, we have to extend this at some point downside and place extend that below part also for connecting VSS, that is ground. That's it. So these are our connections. Okay, source is connected, source of PMOS is connected to VDD. Drain of PMOS and drain of NMOS, they are connected and they are connected to output. And the source of the below, that is NMOS, is connected to ground. Now it's time to apply the supply and ground. So there is a small arrow of VDD supply, just you have to put that. Just a minute. So put something wrong here. Okay. So here I will select the metal once again for this. Yes. Now there is a VDD supply option is present. So you just click on that and place it where you want to place VDD. So I have to place it here for the source. So, and there is option of ground. So that I have to place here. So VSS. Then there is only one input. So input here is nothing but a clock signal. So as a clock signal, we call it as an input, and that we will place on the red color line because there you are applying the input, right? So here you name this, rename this as A and click on assign, and output we are keeping on this line, and connection of drain. Okay, the drain of PMOS and drain of NMOS. So here we are mentioning the output. So for output, there is a option of I, the visible node. So that node you have to take, drag and place here. Instead of S1, we'll mention it as a Y. Click on assign. Okay, after this, there is an option which is called as error check option. So you have to just click on that error check option, design error check option, design rule check option, and see here it has given the error, design rule errors detected. See help design rules. So we have done some mistake in designing. So what that error is, the metal vertical width is less than 3 lambda. So according to the rule, the metal vertical width should be at least 3 lambda. We have discussed in the slide, the same point we have discussed in the slide. So this width is less than 3 lambda. That's why it has shown the error. So this is lambda error. Okay. So while designing, you have to take care of these things. Otherwise, you will get such type of errors. Just let me clear the drawings first. So it has shown here the metal vertical width is less than 3 lambda. So it is called as design rule error. So there is a button called as DRC, design rule checker. So you have to click on that button to see whether you have done any design lambda type of errors or you have used it perfectly. Okay, so let's change that. So let's make it correct. So there is an option of deleting the block. So we'll click on that and that block will get deleted. Once again, we will increase its height. And let's click on this design. So in the below part also we have done the same mistake. Let's correct it. So there is an option of deletion. Once again, select that metal block and select it properly. Once again, click on that DRC button. And now see in the bottom line, it says no design rule error. That means our lambda values are perfect, our spacing is perfect, and our circuit is ready to implement. We can implement our circuit. Okay, so this is how your circuit will look like. Now you have to click on this run button to see the waveform. It will show the warning polarize N well to VDD. So since it is an N well, just a minute. Okay, so here you can see the output waveform like this. Voltage versus time. So see, when your input is high, your output is low. When your input is low, output is high, like this. Okay, so this is between A and Y. So A is the input, Y is the output. So when input is high, output is low. When input is low, output is high. So our CMOS inverter is working properly. So this is how you can implement any circuit in this software, and you can verify. As I said, show palette. So there is option of show palette. So from here you can take the components. Now let's implement the same circuit that we have implemented. Since we are having some more time, we'll try to implement. Okay, so let's click on the file, new. I don't want to save at this moment. Now let's implement the second circuit, that is the NAND gate circuit that we have seen. I will draw the circuit again. So first will come your PMOS. These are your PMOS. NMOS. Then these are your sources, drain, then drain, source, drain and source, and here your output Y. So A, B are the inputs and Y is the output. Now we'll place the components. So here we'll require two NMOS and two PMOS. So first we'll use two NMOS with values, let's say 0, 1 and 0.1. Generate device. So here you have to mention the count. So we'll require 2. That's why I will mention it as a 2. Generate device. Just you have to place it on the screen. So it will create the two NMOS. You can align it properly by selecting it. So just a minute. Yes. Like this. Then select the PMOS with a slice size of little higher. Let's select 2. And the number of devices are also 2. Make sure that you are keeping proper space. Okay, like this. Now we'll connect this slightly on the lower side. Okay. Now connect the two red color lines. If you want to undo, just you have to press Ctrl U. So by pressing Ctrl U, you can undo the step. Then select polysilicon from here. And connect it to NMOS and PMOS. So your first step is taking the polysilicon and connecting PMOS and NMOS. Now the source of now upper is representing the PMOS and lower is representing the NMOS, right? So sources of both are connected where they are connected to VDD. Okay, and the drain is connected to output as well as drain of the A type. So this it is representing the A. The first red color is representing the A, and the second red color representing B. First red color is representing A, and second representing B. Okay. Now we have to extend this metal 1 to VDD. So extend this to VDD. And this is also we have to extend to VDD. Source of the second, that is B type of PMOS, and here there will be a VDD like this. We have kept enough length and width of the metal so that we will not get any design error in this. So both the sources are connected to VDD. Now both the drains, which are representing by below this blue color, they are connected to drain of A. So this blue is representing the drain of A. So we can connect it. We can extend this like this. Just extend it some and extend it and the top. Just we'll see, complete this circuit and we'll stop, okay, because time is also getting over. So this after this circuit we will stop. Extend this like this. Always maintain enough line and width and length, okay, otherwise you will surely get the lambda error. See, the drain we have connected, okay, drain of the PMOS is connected to the drain of A NMOS is connected to the drain of two PMOSes, that is A and B, combining, and then extend this further to show the output. You can extend this further, you can extend this metal further to show the output. So here we will keep or place the output, this metal. Okay, that's it. And then this source is connected to ground. Source of this NMOS should be connected to ground. So we'll extend this metal and we'll extend this. Okay, like this. Now we'll apply VDD. We'll apply VDD here also inside the well. Then we will apply inputs here as A input. We'll give here A. And here we will mention B. And here visible node, that is output. And at last we'll put ground. We haven't checked about DRC rule, just click on that. No design rule error, because we have maintained enough space. So surely we will not get any design error. Now it's time to run. So I will clear the annotation first. Click on the run. Sometimes it will get time to load. Yes. Now see, it is a which gate this is? This is NAND gate. So what is the NAND gate? When one of the input is 0, output is 1, and when both the inputs are 1, output is 0. So see whether you are getting that or not. This is A, this is B, this is Y, right? So when A is high, so this white color is indicated by A, this green color is indicated by B, green color waveform, and the red color, that is output waveform, is indicated by red color. So A is low, B is high, the output is high, right? The first one. Now we can observe from here. So A is low, B is low, the output is high. A is high, B is 0. So for 0, 0, 1, for 1, 0, 1, for 0, 1, 1, and for 1, 1, 0. So it is working properly. You can change the frequency if you want. You can change the step size to view it properly. But for this moment, I'm just showing, I'm not doing any changes to avoid the complications. So you can observe like this also. Okay, so this is the way in which we can design and we can observe. It is very easy to draw a stick diagram on the paper and implement the same on the software. I hope you got a better clarity about this. Still, we are having 10 minutes, so we can have one more circuit. In 5 minutes, I'll just show about the next circuit, that is NOR, CMOS NOR. So CMOS NOR is, so NOR means,
Rahul sir,
yes, yes.
you have applied that VDD to the metal as well as in a well, right?
Yes, yes.
So we need not to apply that VSS to the N well, or it is not required.
We have to apply. It is not required actually, but for circuit, when you are actually performing the fabrication process, that time you have to apply, because otherwise there are chances of the breakdown will happen there.
Okay,
That's
means in
because it is,
this simulation, and so if similarly towards that source of the NMOS we have applied VSS, sorry, ground.
yes,
So
yes.
within that N well also we can apply ground, na?
Within that, below you are asking, right?
Ha.
No, there no need to apply VDD because it is P substrate only. So we
Okay.
have
So in case
already
of
applied.
PMOS only, we need to apply within a well, right?
Yes, within a way. In case of
Okay.
only PMOS.
Okay.
Yes, because it should be reverse bias. So n well, it is n well, so apply VDD. That will be reverse bias. Okay, so let's move to the last circuit. We'll see in 5 minutes. We'll not waste much time. So it is A plus B, that is NOR. So as I said, PMOS, P dot P, apply this logic. So it is parallel, so it should be in series, right? So since it is plus operator, so series AB, VDD, and they are in series, so they are in, should be in parallel. And here is your output Y. So this is source, drain, source, drain, drain, source, source. First you have to draw a circuit diagram, and then only you can process further. First select two NMOSes with one, keep it here. Then select two PMOS with value 2. First, I will move this block. So, I think they are parallel. Okay. Then apply polysilicon. Take once again. I think there is some issue in the software. When I try to zoom in, it is not showing, but actually two apps are running simultaneously, the Zoom app as well as this app. So maybe because of that, otherwise it works fine. So you can try, definitely it will work. Close this once again. Okay, let's take NMOS first with 1 and numbers as 2. Place it here. Then take 2 PMOS with value 2 as a width. Just keep it little. Take care that the distance should be at least the distance should be like that, because while looking at the figure, we will not be able to find out the accurate distance, but just roughly approximately you select the distance so that they will not they will not get overlap, right? So that is the care you have to take. No need to go in more detail about the lambda and all. Okay. Then the first line is A, the second line is B. We'll take metal, we'll connect the A to VDD. And drain and source are connected, and drain of the second is connected to output, and it is also connected to drain of both. So here we will extend this metal like this, and this drain is connected to so here we can have the output. So drain and source, they are connected. Source, the drain of the PMOS B is connected to drain of both the NMOSes, and the source of both the NMOSes are connected to VCC, to the ground, VSS. So you have to just do practice. Practice is the only key for this. Okay, you will not get that in one or two circuit diagrams. You have to practice more. Then last is remaining. Okay, we have done with the connections. So we'll just apply the VDD inside this. Well, then here we'll apply input. Here we'll apply ground. Here we will apply inputs. We'll give name as A. So here we'll give name as B. Here we will give name as output Y. We will check for design rules. Design rule error detected. I think this spacing is small. So we will correct that. So just I will remove that. I will extend this metal Apo, and here I will apply VDD. And now once again we'll check. Now there is no design error rule. Now we can run our circuit. So this is this is NOR gate. So how the NOR gate will work? 1 for 0 0, the NOR gate should be 1. Okay, so for 1 0, it should be 0. For 1 for 0 1, it should be 0. For 1 1, it should be 0, and for 0 0, it should be 1. So it is working properly according to the functionality of NOR gate. When both the inputs are 0, then only the output is 1. Otherwise, output should be 0. And same thing we are getting in the waveform. That means our circuit is working properly. So this is how you can verify and you can observe. Okay, output waveform. There is an option of print also, so you can print the output. Okay, I think we are done with the simulation part also. So I hope you understood this concept. You try this from your side because we don't have this time now. A dot B plus C bar. Okay, so I didn't have that time to make that bar in the presentation, so I written bar. So A dot B plus C whole bar. Okay, so you just try this. You should get this stick diagram. You take the photo of this. So here you have to use, since we are using 3 variables here, A, B, C. So 3 red color lines you will use in stick diagram. Okay, thank you. If you have any question, please ask me. I run my own online courses on VLSI. I take online weekend batches. So these are the various programs, courses are currently going on. So if any one of you is interested, you can contact me personally or in a group you can visit. Okay, I run my own YouTube channel also. There I have posted the courses. Some of the videos are free. Electron ITS. Okay, is my YouTube channel's name. You can visit this Electron ITS. And I have Udemy course on also on Verilog programming. You can, if you want to get some knowledge on Verilog program, you can go for this. And if any one of you is interested, you can contact me on this number. And in today's session, if you are having any doubt, you can ask right now. You can communicate through sir. Okay, sir, this is from my side. If you want to ask anyone.
Okay, students, if you have any query regarding today's session, you can ask to sir right now. Sir, students are requesting to share your PPTs if you can.
Yes, yes, sure. I will share my PPT with you.
Yeah.
I will share with sir. So
Yeah. Anyone has any doubt?
No doubt, sir.
Okay, fine. So thank you, sir, for sparing your time and guiding us in the area of CMOS VLSI design and design rules, stick diagram. The points that you have covered, really, that will be helpful for the students in their curriculum. So once again, thank you. It's really a wonderful session from your side, and definitely our students will be benefited by this session. So thank you.
thank you.